Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. As I was preparing to author a video on creating your own 4-to-1 balun using Coax, a question came up to my mind. The process of making this balun requires an exacting length of coax. So how do we cut this to the right length and still have a way to connect it to our antenna? And I thought, well, how does the shield in the coax affect the velocity factor of the coax? So these questions in my inquisitive mind launched some experiments to try to answer these sorts of questions before I did the video on the 4-to-1 balun. If you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. So let's begin with a starting place. So what is it that made me wonder this in the first place? Well, two things. First, it was my experience in making these 4-to-1 baluns with coax. In the end, the coax always needed to be just a bit longer than calculated to make it really work. Second, it was one of the standard equations for velocity factor, which is 1 divided by the square root of the relative dielectric coefficient of the insulating material around the conductor. So, for instance, I have some coax that has polypropylene as the insulation around the center conductor. The relative dielectric coefficient of polypropylene is 2.2 to 2.4. So the nominal center-of-the-road theoretical velocity factor of this coax would be 1 divided by the square root of 2.3, which comes out to be 0.6594. Well, looking at the coax specifications, we're told that its velocity factor is 0.66. So as I look at this equation, there does not seem to be any dependence on shield or no shield. So this is what is raising the question. Will the velocity factor change if the shield is missing? So how am I going to do this experiment? I'm going to begin with this piece of coax that I've terminated one end with a BNC connector because, well, they're easy to put on. And the other end is cut even with an overall length of 48 1/4 inches or 122.555 centimeters. I will measure the velocity factor of this combination. Then I will strip the outer sheath and shield from the last 4 inches or 10.16 centimeters of the coax. This represents 8.3% of the overall length. If the shield does have an effect on the velocity factor, this should be easily detectable when we remeasure the velocity factor of the assembly. So let's begin the experiment. I'm going to use my VNA for this one because it's easier. First, I have to measure the velocity factor of my piece of coax. I'm going to use the method that I presented in my video on measuring velocity factor using a VNA. I've put a link for this up in the corner for you. This begins by calculating the low and high limits of my scan. The high limit ends up coming out to be 182.5 megahertz and the low limit 30 megahertz. Now that I've calculated and set the start and stop frequencies for the VNA scan, I have calibrated the VNA using my calibration standards. But there's one more step yet to accomplish, however. Because I've terminated my coax in a BNC connector, I'm going to have to use an adapter to accommodate it. This means that I'm going to have to do a port extension to zero out the phase before I make the measurement. Here's how I do it using my VNA, and the process is the same with the Nano VNA, they just use different nomenclature in their process. To set up the port extension, the first step is to put the adapter on the end of the VNA cable. Then we're going to go over here to Format, and we're going to go to Phase. And you can see the significant difference here. the phase is anything but 0 across the whole thing here. We're going to go to scale. I'm going to change the scale to 1 degree per division. Now you can really see it. So now we're going to go to Cal, port extension, and I'm just going to choose 6 because this is pretty long, and apply. Well, 6 clearly is too long, and let's do 5. 5 is closer, so I guess the 5.3, we'll give that a try. Let's move this out of the way. Apply. 5.3 is too much. 5.1. There we go. Pretty much 0 right across the whole shoot and match here, so that's good enough, especially for what we're going to be doing. Now that we have our port extension in place, we can move ahead to measuring the velocity factor of our coax. Having accomplished my calibration and port extension, I will connect my piece of coax to the VNA and determine the frequency for the 3/4 wavelength. So to measure the velocity factor, I have returned the scale to 22.5 degrees per division. That way we can see full 180 degrees to 180 degrees. And what we're interested in are these big transitions here and here, specifically the second one. So I've turned on 2 markers because we are actually interested in this exact spot right there where it crosses a 0. But we're not actually going to be able to get there, so I'm going to take my one marker, put it here at the bottom. I'm going to put the other marker up here at the top, and now I can read my 2 frequencies here at the top corner. So number 1 down here is at 122.2625 megahertz, and number 2 that's up at the top is 123.025. So I'm going to assume that this point right here is halfway between these two. So I'll just average these two to get the number that I want for this crossing point. With that in hand, let's calculate the velocity factor. Our 2 frequencies at the 3/4 wavelength point are 122.2625 and 123.025, which gives us 122.64375 megahertz for the frequency where the phase is at 0 degrees. Now, knowing that our coax is 48 1/4 inches or 122.555 centimeters long, and that the 3/4 wavelength is at 122.64375 megahertz, we can now calculate the velocity factor of the coax. I use the same formula provided in the Measuring the Velocity Factor video. So our unmodified coax has a velocity factor of 0.6685. Now I'm going to strip away the outer sheath and shield of the last 4 inches or 10.16 centimeters of the coax. So now where does the velocity factor lay? So we can see here are the original markers with the coax intact. And now over here I've set up 2 new markers. I have marker 3 here and marker 4 here. And we can see a change in frequency. And so that's going to indicate a new velocity factor. And so now let's calculate that. Well, it did change. We have the new 0 degree frequency of 131.79375 megahertz. And using this and the fact that our overall assembly is 48.25 inches long, we get a new calculated velocity factor of 0.7184. as compared to the fully shielded version, we have a 7.46% change. So the overall effective velocity factor went up. Now please notice that I'm using the term effective velocity factor. Now one thing that we know for certain, the impedance changed drastically between the shielded coaxial portion of the assembly and the simple insulated wire portion. So I asked the question, is the actual velocity factor of the wire portion different than the coaxial portion, or does it just look like it changed because of the effects of the drastic change in impedance? Because the dielectric coefficient of the insulation for the wire portion is the same as the coaxial portion, I surmise that the velocity factor of the wire portion has not changed, and that the apparent change in velocity factor is due to the effects of the drastic impedance change between the coaxial portion and the insulated wire portion. Now, while this is my theory, the actual answer to this question is probably beyond the scope of this video. What does matter is that the effective velocity factor of the overall assembly has increased. And if the effective velocity factor increases, then the overall length of the assembly also has to increase accordingly to maintain the same frequency where the 3/4 wavelength exists. In fact, according to my bench experiment, if the pigtail length is 10% of the length of the calculated the coax alone, then the coaxial portion of the assembly has to be 10% longer than the calculated length with the coax alone to maintain the same overall desired electrical length. Now, admittedly, it's not quite that simple, but it's a starting place. Now, this plays directly into what we will be doing in my next video, creating a 4-to-1 BALUN using coax, and I've put a link to that video up in the corner for you. As you will see in that video, it may be wise to make the coaxial length even a bit longer because the change in the effective velocity factor and the presented impedance due to the addition of the pigtail is not going to be linear. More on this in the next video. Yep, there be a lot of RF magic out there. It has the potential of making the eyes glaze over, the deer in the headlights, well, whatever you want to call it. Now we have some idea of what's going on in this scenario, so we can go on to making our 4-to-1 BALUN. If you found this video helpful, please click on the like and don't forget to subscribe. Thank you so much for watching. Until next time, Toodle-Oots.